Okay, class. I'm back. So it may sound contiguous on the video, but actually did a detour. First of all, I made a failed experiment. I switched my screen to the browser, was hoping the recorder would record whatever I'm seeing, but apparently it didn't. It just still shows the static screen of the PowerPoint, so I'm talking something maybe gibberish to you, but I was actually looking at a web page. But in any case, the second thing is I did find out more about the and immediate and or immediate instructions, because we know in those two instructions the immediate only 16-bit. I was just want to verify what happens to the upper 16-bit. And it's confirmed that in both cases, the upper 16-bit are all 0. Now, if it's there 0, if it's OR operation, that just means it does nothing to the upper 16 of S1. So whatever upper 16 bits in S1 will be preserved in S0. And the lower 16 will just do an OR with this number and put into lower 16. Now, with 0, you know AND basically cleared it up. So after this operation, the upper 16 of S0 was going to be all 0. The reason is because the upper 16 of this imaginary 32-bit operand is all 0. So that's an interesting detail that I wasn't sure. That's why I went back and checked. You know, I think I might just present this way. It might help better. So let's continue to review what we learned last session. We talked about 3 different branch instructions. One is if those 2 registers are equal, you jump to a label. If it's not equal, you jump to a label, or you just unconditionally jump to a label. So we used this example to show, check on these 2 variables. If it's yes, you do this. If it's not, you do that, and then we see that you compare that. And if they're not equal, you go to else, which does the subtraction. If it doesn't jump, that means they are equal. So it will do addition here. But after doing addition, you don't want to do subtraction, so you do a jump to the one after subtraction. So there's 2 labels here. This shows how the translator or the compiler will translate into high-level languages like this into assembly code. So we also showed an example how to do a loop. In this particular case, it's looping through an array to check if there's an element equals to k. And because the array is an integer array, each element is 4 bytes. So the I, which is in S3, needs to multiply by 4. And we know if we're going to shift the bits by 2 to the left, it's equivalent to multiplication of 4. So once we get the offset multiplied by 4, that represents the bytes, offsets in bytes, and we can add to the base address of save. In this particular case, it's S6. So S6 plus T1 and put into T1, and then we can load the content of that address into T0, and then we can compare. And if it equals K, which is stored in S5, then we exit the loop. Otherwise, we increment I by 1, and then it goes back to this. So we skipped this, so we're going to continue to skip this. Here, I don't think we talked about this, so now we're going to continue and talk about more conditional operations. So one of the operation is it's called a set on less than instruction. What it does is, if this second register is less than the third register, you would have set 1 to the destination register. So the C code would look like this. If R is less than RT, RD equals 1, else RD is 0. Now the third one, it has an immediate form, can be a constant. So if RS less than constant, RT is 1, otherwise RT is 0. If you just set the content of register, so it doesn't affect a PC, the program counter. But it's not very useful. The most useful thing is to actually you take some action on the result. So most useful combination is you combine them with B equal or B and E. So in this case, you're saying if S1 less than S2, you would have set T0 to 1. Now, if T0 is not 0, which means when it's 1, then you would, you compare this to be 0 now. If they're not equal, meaning this is not 0, then you jump to L. That means, T0 is only 1. It only became then 0 if S1 is less than S2. So basically, there's two things says if S1 less than S2, you jump to L. It's pretty obvious. Now, the question being asked here, wow, so if this is like seems you need 2 instructions to do one thing, why don't you have an instruction called, if it's less than that, you just jump, like BLT, right? So BLT, BG. Well, the reason is for performing the greater than or less than or equal to is slower, and branching instruction is even slower too. So combine those 2 complicated operations together into one instruction, you will create one very complicated instruction. Remember, CPU has cycle has a period. If you somehow create a very complicated instruction that requires very long clock period to execute, then all instructions have to take that prolonged clock period. Then the whole machine gets slower. That's the rationale, because clock period is fixed. You don't vary from instruction to instruction. So that's the design trade-offs here. You just split one complicated instruction possibly into 2, but then the whole machine's clock period is smaller. Okay, so there's 2 versions for comparing less than, signed and all unsigned, because it has very different results when you compare less than. So I didn't look at the examples. What is the example trying to say? Oh, this is 0 and this is -1. If this is signed. If this is unsigned, this is a very big unsigned number. So if you compare signed, then this is -1, less than 0, which is true. So T0 will get 1. Now, if it's unsigned, you put a little U there. This is not less. This is not true, and this is a very big number. So T0 is 0. Let's see. What is Oh, now we're gonna just to make you feel at home, we're gonna take a look of the encoding of the instruction of those instructions. Branch on equal. You notice the this is the what format of this is. You should be able to tell this is I format. 16-bit lower 16-bit contains the immediate numbers, and then there's 10 bits contains the encoding for the two registers, and then the opcode is the first 6 bits. And one thing you notice the semantic is if these two registers are equal, you advance PC, set PC to offset left shift by 2. What does that mean? That means this immediate number represents not byte, it's word. Why? That's because in MIPS, every instruction has 4 bytes, and it's always aligned. What does that mean? That means the instruction address, the last 2 bits of instruction address is always 0. That's the only way you get aligned in memory by 4. So instead of storing the immediate offset with the last 2 bits always being 0, which is really wasteful, in this particular case, offset is you just don't store the last 2 bits, and when you actually try to change the PC, you will times 4. And notice this is also a signed number, so if it's negative, you will jump backward, and if it's positive, you jump forward. It gives wider range of jumping. And same thing for the BNE. Oh, I made a mistake, did I? If not equal, yeah. What it really says is BE, BN. Okay. So this is a new encoding format we have not really learned so far. It's an unconditional jump. As you can see, this first 6-bit is operation code, and the rest 28 are all a constant number. And in this particular case, what it's trying to do is you have to get around your head a little bit. It's try to changing the PC. How does it changing the PC? If first the new address of PC conforms of 2 parts. The first 4 digits are taken from current PC, and then the rest of 28 bits come from 26 bits here, and then do a left shift by 2, and the last 2 bits will be 0. So by doing this, you will have a new PC. That's where you're jumping to. This is called a pseudo. Later on we will see the summary. This is called a pseudo addressing. Basically, you can, with 28 bits, you can jump very far, but it's constrained by a region. It's about 256 meg, I think, where the PC is. So you stay in the same region. As long as you're in the same region, you can directly jump into that area. Okay, so that actually I'm sorry, let's get into the next section, subroutines and branching. Subrouting and branching, a special case just of the branching we talked about earlier. Subrouting is function calls. There are several steps to complete the function calls. First, you put parameters to registers, and then you transfer control to procedure. What does that mean? It means you change the PC value to the beginning of that function, the subroutine. And then inside the subroutine, acquire storage for procedure. What does that mean? That means if you have local variables, you will put them into stack, do the initialization, save some stuff. And then you just do the normal thing you would do in a subroutine. And eventually, before you return, you put the results in the register for color. What does that mean? You basically put into V0, and then you jump back to the color, to the return address, the address caller wants you to return to. And it usually is the one immediately after the call. So we will see some examples here. Here's just a review of the registers related to the function call. A0 to A3, that contains the arguments you pass to the function. Again, if it's less than the number of arguments less than 4 or equals 4, you just put into register. And register 2 and 3, V1 and V0 are used for result. For C functions, it's only V0. T0, T9 are so-called temporary scratch registers. That means the subroutine are free to use them without worrying interfere with the caller. And S0 to S7, by the way, that's what the S stands for. It needs to be saved. That means if subroutine wants to change them, you better save them, because otherwise the caller may have some useful information there. You change them, you do your job, you come back, and the caller will be screwed up. So this is the difference between S0 S register and temporary registers. This one caller guarantee that there's nothing useful in it when I call you, so you are free to use them without worrying too much. But this one basically saying, no, you don't touch them. If you really have to touch them, you save them first, and then you can touch it. But before you return to me, you got to restore the original value, so that to me, to the caller, the content is the same. You have to agree with this. This is a protocol between caller and the callee. GP is the point for static data. Basically, the global data is a base point of a global data. Then you can just assign some offset to access the global variables. SP is for stack pointer. We're going to look a little bit more. FP is for frame pointer. We look a little bit more later. And then RA is the return address. The first important instruction is called JAL. It's called a jump and link. And then you pass a procedural label. What does procedural label mean? This is basically first instruction of the subroutine. That's the address. So you just jump to that. Well, you were saying that seems to be the same as the J instructions. Jump to that label. No. It's similar, but it does one more thing automatically for you. The address of the following instruction right after this instruction is automatically put into RA. It just automatically does that. Now, why that's important? That's because after you call this, RA have the address right after this instruction. Now, that's exactly you want the callee to return to. After callee finishes its job, you will do a JRRA, which is exactly say here, and that will get PC to execute the instruction right after this one. That's what you want. When subroutine finishes, you want to continue your execution right after the calling instruction. So okay, so I think there's now we started with the example. It's called a leaf example because this function doesn't call any other function. So this kind of function is called a leaf function. This function takes 4 arguments. By the way, this is syntactically wrong. He has to put int here, and int here. Otherwise, you will not even compile. And this font is a little bit horrendously big. Let's make it smaller. Okay, that looks better. So because the arguments only 4, they're just put into the A0 to A3. F is assigned to S0. This is just to create a situation. You will see how that works. It doesn't have to. You know, if you use T0, then you don't have to bother. But I guess this example wanted to show you, you know, if you do want to put an F into S, now you have to obey the convention. S callee have to save it. So let's look at the example here. By the way, so this is local variables. So you need to involve stack. So here, what they're trying to do. The first instruction is it add with -4. That means it's decreasing this SP pointer by 4. When you decrease the SP pointers, now I wish I have a board. I can draw the picture, but I'll try to talk. See if you remember, we said the memory is a giant array. Imagine an array drawing on the whiteboard. The lower address is at the bottom, higher address is at the top. The stack grows from the top to the bottom. So when you reduce SP by 4, you're moving the stack pointer downward by a word. That's allocating local space. So when you do that, you suddenly have 4 more bytes you can work with. Nobody has used. So in this particular case, the code is storing S0 into that space. Now the reason why it has to store S0 is because he has to use S0 for the F, as we talked about earlier. So what he's doing, the code is, let's see, sorry, not this one. Code is to basically add first 2, add the third and fourth, and subtract, okay, and then return. So he's adding first 2, and then he's adding third and fourth, and then he just doing subtraction, putting into S3. Well, you put it into S3, that's not very useful because you want to return it, right? Look, you're going to return F. So in order to return it, you have to assign S0 to V0. There's no such a move instruction, but you can do an add with 0. That's basically move the constant to this one. As you can see, you already see the stupidity of the compiler here. I mean, if you really want to just put into S0, why do you use S0, V0? Why do you use S0 at first place? You could just set this to V0 and forget about all this hoopla of, you know, allocating a space, and also later on you have to restore S0 from the stack, and also changing the SP register and before you return. So basically all these instructions, 1, 2, 3, 4, 5, all these 5 instructions are not needed if you only change this S0 to V0. Yes, a good compiler would do that. Most compilers would do that. I think this one is just want to show you an example with a stupid compiler where, you know, you make a decision that S0 has to hold F. Then this is what you have to do if you make that decision. You have to allocate a space to store S0 because caller will need this value. And then before you return, you gotta restore the value of S0 from stack, and then restore the stack, and then return. So I hope that shows a little bit more complicated examples. Earlier we were showing the simple ops. It was a very simple function and doesn't involve a stack, and we just directly use V0 as a return. So now this is a little bit of a complicated case where there are more things going on. So this is a leaf. What we saw is the leaf functions. What is non-leaf functions? Non-leaf functions, inside the function, you have to call other functions. So there is a special case of non-leaf functions, means it calls itself. That's called a nested call. Caller must need to save on the stack its return address, arguments, temporaries needed after the call. Remember, you have to send temporaries because your callee, the one you're calling into, may change it without restoring it. So if there's something useful for you, you want to use after the calling, then you need to save it yourself. And any arguments, meaning A0 to A3, if you're still hold on to them, won't use them, you need to save it. So, but for any contents put into S register, S0 to S7 or S8, you don't have to worry about it. The content there is guaranteed to be there after the call. So here is another example. It's compute factorial in C code. A factorial is just the multiplications from 1 to the number. So factorial 5 would be 5 times 4 times 3 times 2. This should be 120. So C code is a nested call. You pass n, the one you want to compute first. If n already reaches 0, you just return. Wait, something is wrong. I think you should have returned 1. Why is return F? Right? Yeah, should be. If it's 0, you return 1. In fact, if it's if it's 1, you should also return 1. But I guess it goes all the way to 0. So if it's 1, you will return 1 times 1. So it's still 1. And that's fine. So basically, if it's greater than or equals to 1, you will the number itself and times factorial of that number subtracted by 1. So arguments of n is in A0, return is in B0. So that's what's expected. So let's see. Again, this probably stupid compiler. Let's see what they compile. So first of all, we notice it's decreasing stack pointer by 8. That means it try to allocate space for 2 variables, 2 items. The first one is putting A0 there, which is the arguments. And actually, first thing from the bottom. And the second thing you put is the return register. Why does the return register? Because later on, you're going to call yourself. When you call yourself, remember JIL instruction will automatically save next instruction address into RA. If you don't save it now, after you call another one, your RA is screwed. Later on, when you call JRRA, that's the wrong number. That's a wrong address. So you need to save it, and somewhere I have to restore it, like you see here. But let's worry about that later. Okay, so here, what you're testing? You're testing A0 against the 1, see if it's less than. If it's less than, this will become 1. But if it's 0, that means, hey, it's not less than. So you jump to L1. Yeah, well, I'm confused. So if it's less than, if it's, wait a second, what's happening? So if it's equal, you jump to there. That means it's not less than. You do a recursive call. But it's indeed less than, and this will be 1. So you will do this. What do? You set 1 to V0, and then you increment SP by 8, and you just jump RA. In this case, you didn't return a register from stack because in this pass, RA has not been changed yet. So you are good. The RA is still holding the right value you want to jump into, so you just call return. Now, if it's equal 0, that means that this is 0, and that means you are not less than 1. In that case, what do? You decrement A0 by 1, this is n minus 1, and you jump into factorial again. That means you call yourself. That's a nested call. And remember, in doing this, RA is set to the next instruction, which is this one. Okay, so somewhere there should be a multiplication. Okay, so after you call this, it comes back. So really, this is really bad compiled, I have to say. So logically speaking, what it really should be doing, you should execute this instruction. Again, because I have to restore. I see. So anyway, he's now restoring the A0, which is stored here, and he's gonna restore RA, and then he restore SP. Now with the correct A0 and also the return from the function called V0, these two times multiply by each other, and it will put into V0 and RA, so it will return. Again, if this is a nested call, you will return to here. So you will do the restore and just keep doing this until it goes all the way from 1 to 2 to 3 to, in our case, to 5, and it will be to the main routine. This could be a little bit complicated. I wish I can explain that in person. But now we have to do with this. Just glaze at this a little bit. Try to imagine what is happening there. I think the next picture will try to explain that. Let's see if we can do that successfully. Now I'm going to take a little break here to see, just to make sure everything is right. Actually, no. Let me finish this section. Yes, let's finish this slide. I'll take a little mini break. So this one try to explain what's happening on the stack. This is the picture I want to draw. You have lower address, higher address. Basically, as you can see, when you jump into a subroutine, you move the stack pointer down here. Once you move down, remember this is an unused area before. So now suddenly this area you can start to use, and you can use this as a base register. You can just add an offset 4, 8, 12, whatever you safely allocate. And this is the place you put saved arguments register. In our case, you saw A0 was saved, and then save the return address. You also saw that. If you're not leave functions, you definitely need to do that because you're going to call other functions. RA will be destroyed in that instruction. So you possibly also save something for S registers. And then if you have local variables, this is where it is. And then before you call JR, RA register, basically return, you should restore SP back to the original case, basically caller case. Then when you restore, basically it goes back to the caller. function, and that's what the caller function do. That's what they expect of their SP, so he didn't change anything. It's a little bit convoluted. You really take some thinking to understand what is happening. So we talked about this before. You have a text section where you have code, and then you have global variables, and then you have dynamic data, which is malloc, and then you have stack to grow from the top to the bottom. So this is the memory areas. And I'm going to take a small break here.